Welcome to the lecture on forced vibration under Coulomb damping. So far we have discussed the case of the viscous damping. Now when we have Coulomb damping in the system, it means that there is some mass that is moving on some surface, some dry surface, and there is friction between the two surfaces. So there will be some energy dissipation, and if we have this type of damping, what will be the response of the system? Okay. So there is some easier ways to study this kind of systems. One is that we convert this kind of damping, like Coulomb damping, to an equivalent viscous damping. How and why it can be convertible? So first, why? So because the basic function of damping is the energy dissipation. So in a viscous damping case, there is some damping in the slow movement of some piston in the fluid. This kind of damping is regarded as viscous, and there is energy dissipation. But in friction also there is energy dissipation. So if we can get that how much energy is dissipated in each cycle of a Coulomb damping system, and we equate this energy to the energy dissipated per cycle of a viscous damping system, from there we can get the equivalent viscous damping coefficient, and if we get the equivalence, we can use all the expressions and all the equations that we derived for viscous damping. So therefore we are going to do this study with of the Coulomb damping with the converting it into an equivalent viscous damping system. So let's take a system so we have a spring mass system that is moving on a dry surface, and there is some force applied, that is F0 sine omega t, the harmonic force. So if we can write the equations of motion for this kind of system, so equation of motion mx double dot plus cx, sorry, not c but plus kx, and here it is plus minus f equal to f0 sine omega t. So F is mu times m into g, that is the frictional force. So there is plus minus sign, and this because the friction force depends on the direction of the relative velocity. It can be positive. So here the plus sign, positive sign is taken when the mass moves from left to right, and we take negative sign when mass moves from right to left. Now we want to solve this system, and as I said that we will use the equivalent viscous damping concept. So first we have to know that how much energy in case of Coulomb damping is dissipated in every cycle. So we know that this mass m is moving against some frictional force F, and this mass, first it is moving here the maximum displacement, let us say x, then again coming back to its equilibrium position, it is moving here x, then again going here the maximum, that is x, and again coming to this equilibrium, so moving x. So it means that this mass is moving in one cycle. So one cycle is complete when it start from here and reach at the same point, but in this one cycle it is moving by 4x. So 4 times x, because in quarter cycle it is moving the maximum amplitude x, and during its movement there is a constant friction force acting on the system. So the work done by this friction force or the energy dissipated per cycle equal to 4x into F, that is 4Fx in case of Coulomb damping. Case of Coulomb damping. Now we know that in case of a viscous damping system, the energy dissipated per cycle is pi c omega x square. So energy dissipated per cycle in a viscous damping system equal to pi c omega x square. So it means we are going to convert this system into an equivalent viscous damping system. So this is mk and here is c equivalent, and this is f0 sine omega t. So we are going to convert this system into this system, and here we say c equivalent because we are going to convert equivalent viscous damping for the Coulomb damping case. So now we equate this equation number 1 and 2 because we are equating the two energies per cycle. So pi c equivalent omega into x square equal to 4 times fx. This means c equivalent equal to 4f upon pi omega into x. So this is the equivalent viscous damping. Now if we have the equivalent viscous damping here, we can use all the expressions that we have derived for the viscous damping case. So the basic thing is we want to know the x, that is the amplitude, and in this case we have our equation of the response of the system x equal to x sine omega t minus phi. So here x equal to f0 by k. So it is f0 upon root k minus m omega square whole square plus c omega whole square under root, or we can write f0 by k 1 minus m omega square by k whole square plus c omega by k whole square under root. Now here C is, now it is C equivalent. So here we can put C equivalent. Here also we put C equivalent, because now our C is C equivalent. And now we can write here x by f0 by k equal to 1 upon 1 minus omega square by omega n square whole square plus, we can put here C equivalent value here. So C equivalent into omega by k equal to 4f by pi omega x into omega by k. So omega will cancel out. We will get 4f by pi x k. So here we will get 4f by pi k x square under root. Okay. Now this equation we have to solve. So we, because x is here and x is also here, so we have to take out this x in one side. So we square these to both sides. So we will get x square by f0 by k square into, so this under root, so it will be just like 1 minus omega square by omega n square whole square plus 4f by pi k square into 1 by x square. Equal to 1. So we will have x square by f0 by k whole square 1 minus omega square whole square plus so x square here will be cancel out, and here will be 1 by f0 by k square, so it is k square by f0 square, and that is equal to 1. And here is, this is also k square, so this k square will be cancel out. So we will have we may have this this term will be as such plus 4f by pi f0 whole square equal to 1. Now we take this other side, so it is 1 minus 4f by pi f0 square, and that is x square by f0 by k square upon 1 minus omega square by omega n square whole square. So here we got C equivalent equal to 4f by pi omega into x. So we can find x upon f0 by k equal to maybe plus minus under root 1 minus 4f by pi f0 whole square upon under root 1 minus omega by omega n whole square. So this will be under root will be here we will have, because we have a squared, so we will have only this term. Okay. So this is the x that we get the response of amplitude of the response of this Coulomb damping system. Now we see that to have a real solution, that is the solution that is not complex, we must have this under root quantity must be greater than 0. It means that 4f by pi f0 should be less than 1, because if it is less than 1, then only this 1 minus this quantity will be positive. So it means that 4f is less than pi f0, or pi f0 is greater than 4f, or f0 by f is greater than 4 by pi. So these are the conditions. We can see that f0 should be greater, because f is the frictional force and f0 is the amplitude of the external harmonic force, and it demands that to have some harmonic motion, this external force amplitude must be greater than 4f by pi. Now this condition must be satisfied to have the real values of x. Now what is phi? Phi is the, so we know that phi is tan inverse 2 zeta r upon 1 minus r square, and here zeta is zeta equivalent, and zeta equivalent equal to C equivalent by Cc, and C equivalent we already know 4f by pi omega x into 1 by Cc is 2m omega n. So this will be 2f by pi m omega n into x. And r is omega by omega n. Okay. So we can get the phase. Now if we want to know what is the energy dissipated, so we can plot. So this is the energy dissipated per cycle, and this is I think x. So energy input, energy input in the system is, as we have already derived, pi f0 x sin phi. So at phi equal to 90, the resonance condition, we have it is pi f0 x, and if we plot this energy input, so this is the energy input at resonance, and this is pi f0 x, this is x. So here this is the slope, so this is pi f0. Now energy dissipated is in Coulomb damping is 4Fx. So it is here, this is energy dissipated in case of Coulomb damping, and this is the slope 4F. So we see that the slope pi f0 should be greater than 4f, and that is what conditions we are getting from here. Pi f0 is greater than 4f. It means the energy input will be greater than the energy dissipated. Okay, so let's see one numerical example. So based on this, so it is said that there is a horizontal spring mass system. So we have made this system here that is subjected to dry friction damping and has the following physical data. So mass is 3.7 kg. So here we have m equal to 3.7 kg. Spring constant K equal to 7550 Newton per meter. Coefficient of friction between the mass and the horizontal plane is 0.22. The mass is subjected to a sinusoidal forcing function of amplitude 19.6 Newton. So amplitude of the force F0 equal to 19.6 Newton. So F0, and the frequency is 5 Hertz. So here omega is 2 pi into 5. Now find the amplitude of vibration of the mass. Also calculate the equivalent viscous damping. So first we have to find the amplitude of vibration of the mass. So we can use this formula to find the amplitude of vibration, because we have to find the x. First x equal to constant, then C equivalent. The equivalent damping, viscous damping is required. So here what we have to find, first in this expression we have to find f first. F equal to mu times m into g. Mu is 0.22 into m is 3.7 and g is 9.8. So we will get some this. So we get So we get 7.98 this frictional force. Now we have to get the omega n. So omega n is root k by m. So that is equal to under root 7550 by 3.7. So that is 45.17 radian per second. Now we put these values. So x by f0 is 19.6 upon k is 7550 equal to under root 1 minus 4 into f is 7.98 upon pi into f0 is 19.6 square of 1 minus, so omega by omega n, so omega 2 pi into 5 by omega n is 45.17 square. So we can calculate so this is coming 0.516 and the top one to 0.855. So x equal to into, and this will be multiplied 19.6 by 7550. So it is about 4.3 into 10 power minus 3 meter. So it is equal to 4.3 mm. So we get the amplitude of vibration of the mass that is under the Coulomb damping. Now we have to find the equivalent viscous damping. So equivalent viscous damping, we know C equivalent equal to 4F by pi omega x. So 4 into F, so F is 7.98 upon pi into omega. So omega is here 10 pi into x. X we have already calculated 4.3 into 10 power minus 3. So we can find so it is coming to be 75.17 Newton second meter. So thus we understand that to solve the case of the Coulomb damping, we can convert it into the equivalent viscous damping, and then all the expressions that we have derived for the viscous damping can be used here, and we can find the amplitude of vibration of the system. So thank you for the attention to this lecture, and see you in the next lecture. Thank you.